It's amazing to think about, isn't it? How much we all rely on software in our daily lives. I mean, it's practically everywhere.
It really is. Everything from the apps on our phones to the systems that run our banks, hospitals, and even our cars.
Right. And sometimes it works so seamlessly that we barely even notice it. But other times, well, let's just say we've all experienced the frustration of a software glitch or two.
Absolutely. We've all been there.
Yeah.
And that's exactly why we're here today to pull back the curtain on the world of software development and explore what goes into making sure that smooth, reliable experience is the norm, not the exception.
Exactly. This is our deep dive into how software gets built and, just as importantly, how it gets tested to make sure it actually works as intended.
And you, our listener, you're the one who ultimately benefits from all this effort.
Right, because we all want the software we use to be reliable,
Right.
to do what it's supposed to do, without crashing or causing us headaches.
Precisely. So we've gathered a bunch of really interesting information here, a wide range of sources that cover all aspects of software testing and development.
We're talking about different stages of the development process, the various roles involved, the different types of testing that are performed, and the key principles and techniques that guide this whole complex endeavor.
Our mission today is to distill all of this information, to extract the core concepts and practical insights, and hopefully equip you, the listener, with a better understanding of how software is created and how it's ensured to work correctly.
So let's jump right in. First things first, we need to establish a common understanding of the basic concepts.
Right, the foundation. So, in simple terms, what exactly are we talking about when we say testing? What does that actually involve?
Well, you can think of testing as a sort of digital quality control check. It's the process of carefully examining a software product, putting it through its paces, so to speak, and comparing its actual behavior to what it's supposed to do.
And those expectations, those supposed to do aspects, that's where the concept of requirements comes into play, right?
Absolutely. Requirements are essentially the detailed specifications for the software. They spell out exactly what the software product needs to accomplish.
It's like the blueprint or the recipe for the software.
Exactly. They define the features, the functionality, how the software should interact with the user, and all the essential details that determine how the final product should behave.
And when there's a mismatch between what the software actually does and what's laid out in those requirements, what's the term we use for that?
That's when we encounter the dreaded bug, or to use a more formal term, a defect.
Right. It's basically any deviation from those intended specifications, a place where the software doesn't quite do what it's supposed to do.
It could be that it does something it shouldn't, or maybe it's missing a feature it was supposed to have.
And who is the key player, the specialist, whose primary responsibility is to identify those bugs and ensure the software aligns with those requirements?
That would be the tester.
The quality champion.
Exactly. The tester is the one who meticulously scrutinizes the software to verify that it's not only working correctly from a technical standpoint, but also meeting the needs of the customer and fulfilling its intended business purpose.
Now, I know you mentioned earlier that there are different types of software. Could you give us a quick overview of some of those different areas?
Oh, absolutely. The world of software is vast and incredibly diverse, and testing approaches definitely need to be adapted to the specific type of software being developed.
Of course, you wouldn't test a mobile game the same way you'd test, say, banking software.
Exactly. So some of the main areas we're looking at here are web applications, the kind you access through your browser.
Right, the websites and online services we use every day,
Then there are mobile apps, those specifically designed for smartphones and tablets.
with their unique interface challenges and touch-based interactions.
Then we have video games, a whole world unto themselves with complex rules, graphics, and user experiences to consider.
And don't forget about embedded software, the software that runs on all sorts of hardware devices.
Right, from household appliances to medical equipment and even cars.
And then there are the more traditional desktop applications designed to run on personal computers.
Each of these areas brings its own unique set of testing considerations and challenges.
So now that we have a handle on those basic concepts, let's dive into the process itself. How does this testing journey unfold from start to finish?
Well, that's where the software testing lifecycle, or STLC, comes into play. It's essentially a structured roadmap that outlines the step-by-step process for testing a piece of software.
A roadmap to ensure quality.
Exactly. And it consists of several key stages.
Walk us through those stages. What's the typical flow of activities in the STLC?
Well, the first stage is requirements analysis. This is where the testing team really digs into those requirement documents we talked about earlier.
Making sure they have a crystal clear understanding of what needs to be built.
Exactly. They're looking for any inconsistencies, ambiguities, or potential conflicts in the requirements.
Anything that could lead to misunderstandings or misinterpretations down the line.
Right, because it's much easier to iron out those issues early on in the process than to try and fix them later when they've manifested as bugs in the code.
Absolutely. It's all about prevention rather than cure. So what's the next step in this life cycle?
Next up is test planning. This is where the testing team develops a comprehensive plan for the entire testing effort.
The master plan for the testing operation.
Exactly. This plan outlines the scope of testing, the timeline, the testing methods and techniques that will be used, and the resources needed to execute the tests.
So they're essentially creating the blueprint for the entire testing phase.
Precisely. Then comes test case writing. This is where things get really specific. The testers actually design and document the individual test scenarios.
Thinking of all the different ways users might interact with the software.
Exactly. They consider all the different inputs, actions, and sequences of events that a user might perform.
And for each of those scenarios, they outline the expected outcome, what the software should do in response to those actions.
Right. They're essentially creating a detailed set of instructions for how to test each aspect of the software.
And part of this stage also involves preparing test data, right?
Oh, absolutely. That's a crucial part of it. Test data is basically the information that's used to simulate real-world usage patterns.
So it might include things like creating test user accounts with different roles and permissions, or setting up specific data sets that mimic how users would typically interact with the software.
Exactly. The goal is to make the testing as realistic as possible. So once those test cases are all documented and the test data is prepared, what happens next?
Well, before those tests can be executed, you need the right environment to run them in, right?
That's right. That brings us to test environment setup. This stage involves getting the necessary infrastructure in place, the servers, the software, the configurations, to create a stable and controlled environment where the tests can be run.
So essentially a mini production environment specifically for testing purposes.
Exactly. And increasingly, this involves setting up cloud-based environments, which offer a lot of flexibility and scalability.
The DevOps team often plays a critical role here, right?
Absolutely. DevOps, which is a set of practices that emphasizes collaboration and automation between development and operations teams, is really instrumental in streamlining the process of setting up and managing these testing environments.
Makes sense. So once the environment is ready, it's finally time for the actual testing to begin, right?
Yes. Test execution is the stage where the testers actually run those meticulously crafted test cases. They interact with the software, following the steps outlined in each scenario, and they carefully document the results.
They're essentially checking whether the actual outcome matches the expected outcome for each test case.
Exactly. And finally, we reach the closure phase. This is where the testing team analyzes the results of all the tests, documents any defects that were found, and determines whether the software meets the defined quality standards and is ready for release.
So if all the tests pass and the software behaves as expected, no critical bugs, then it gets the green light to move on to the next stage of the development process.
Right. But if significant bugs are discovered, then the software gets sent back to the development team for fixing and retesting. It's an iterative cycle of test, fix, and retest until everything is working as it should.
So that's the journey of a piece of software through the software testing lifecycle. But this testing process, it's not just a standalone activity, is it? It's part of a much bigger picture.
Right. It's one piece of the puzzle.
Exactly. It's all part of the broader software development lifecycle, or SDLC, the end-to-end process of planning, designing, building, testing, deploying, and maintaining software.
So the SDLC focuses specifically on the testing activities, while the SDLC encompasses the entire software development journey.
And the SDLC, it's not just about getting the software built, it's about doing it efficiently, effectively, and in a way that minimizes risks and ensures the final product truly meets the needs of the customer.
Absolutely. A well-defined SDLC is really crucial for successful software development.
What are some of the key benefits that a structured SDLC brings to a project?
Well, for starters, it brings much-needed clarity and transparency to the entire process. Everyone involved, from stakeholders to developers to testers, has a shared understanding of what's happening at each stage.
It helps to avoid surprises and keeps everyone on the same page.
Exactly. And that leads to more accurate estimates of project timelines and resource requirements.
Which in turn helps with managing costs and minimizing the risk of delays or budget overruns.
Right. A well-defined SDLC also fosters a more systematic and predictable approach to software development.
So there's less room for chaos and ad hoc decision-making.
Exactly. And because the process is more structured and controlled, the quality of the final product is likely to be higher, which ultimately translates into greater customer satisfaction.
So it's a win-win for everyone involved. Now, can you walk us through the typical stages that a software project goes through as part of this SDLC?
Sure. It typically starts with the planning phase. This is where the initial groundwork is laid, defining the project scope, setting goals, and conducting a thorough analysis of the costs, benefits, and potential risks.
So they're figuring out the what and the why of the project.
Exactly. And a really critical part of this phase is gathering all the requirements from the various stakeholders, the customers, the end users, the business analysts, everyone who has a vested interest in the software.
These requirements then form the basis for a detailed software requirements specification, document the essential agreement that guides the entire development process.
Right. Once the planning is complete, the project moves on to the design phase. This is where the software engineers take those detailed requirements and translate them into a concrete plan for how the software will be built.
They're essentially creating the architectural blueprint for the software, right?
Precisely. They're deciding on the technologies to use, the programming languages, the database structure, and all the technical details that determine how the software will be implemented.
So they're figuring out the how of the project.
Right. And then comes implementation, the stage where the actual coding takes place. The developers write the code, build the various components of the software, and bring the design to life.
And as we discussed earlier, the testing activities run parallel to this implementation phase, right?
Oh, absolutely. Testing is an ongoing and iterative process that's tightly integrated into the development workflow.
Developers are constantly writing and testing their code, and dedicated testing teams are working in parallel to verify that the software is meeting the requirements and functioning correctly.
Right. Once the coding and testing are complete and the software has been deemed ready for release, we move on to the deployment phase. This is where the latest version of the software is carefully moved to the production environment, the live system that end users will actually interact with.
So this is where the software goes live.
Precisely. And then finally, we have the maintenance phase, which is an ongoing process that encompasses all the activities involved in keeping the software running smoothly and up to date after it's been released.
This includes fixing any bugs that might crop up, responding to user feedback, making necessary updates and enhancements, and monitoring the overall performance, security, and usability of the software.
Right. It's all about ensuring that the software continues to meet the evolving needs of its users over the long term.
So we've covered the software testing lifecycle and the software development lifecycle. Now, I understand there are different models or approaches to managing these life cycles, right? Not every software project follows the exact same structure.
Oh, definitely. There are several different SDLC models, each with its own unique philosophy and set of practices.
What are some of the most widely used SDLC models?
Well, one of the earliest and perhaps most traditional models is the waterfall model. As the name suggests, it follows a linear sequential approach. Each stage of the SDLC is completed in a strict order, with no overlap or iteration. You essentially move from planning to design to implementation to testing to deployment and finally to maintenance, one step at a time.
So it's a very structured and rigid approach.
Exactly. And that can be a benefit for certain types of projects, especially smaller, well-defined projects, where the requirements are clear from the outset and unlikely to change significantly.
But it's not very flexible, is it?
No, not really, and that's one of its main drawbacks. If the requirements do change mid-project, which happens quite often in the real world, then the waterfall model can become quite challenging to manage.
Makes sense. So what are some other models that offer more flexibility and adaptability?
Well, the iterative model takes a different approach. Instead of one long sequential cycle, it breaks down the development process into a series of shorter, more manageable cycles called iterations.
Each iteration essentially produces a working version of the software, or at least a part of it.
Right. And the beauty of this model is that you can get feedback on each iteration and incorporate that feedback into the next cycle.
So it's a much more iterative and feedback-driven approach.
Exactly. And that makes it easier to adapt to changing requirements and to course correct if things aren't going as planned.
And what about the spiral model? That sounds quite intriguing.
The spiral model combines elements of both the waterfall and iterative models, but it places a very strong emphasis on risk management.
Risk management is crucial in software development, isn't it? Things can go wrong in so many ways.
Absolutely. So at each stage of the spiral model, the team conducts a thorough risk analysis, and often creates prototypes to help mitigate those risks.
So it's a more cautious and measured approach.
Right, and it's particularly well suited for larger, more complex projects where there's a higher level of uncertainty or potential for things to go wrong.
But it can also be more time-consuming and resource-intensive.
Right. Yes, it can be, especially for smaller projects where the risks might be more manageable.
And for Annalie, we have Agile, the buzzword du jour in the world of software development. What's the essence of Agile?
Agile is a philosophy, really. It's a way of thinking about software development that emphasizes flexibility, collaboration, and rapid iteration.
It's all about embracing change and responding quickly to feedback.
Exactly. Agile breaks down the development process into short, time-boxed cycles called sprints, typically lasting just a couple of weeks.
And during each sprint, the team focuses on delivering a small, working piece of functionality.
Right. And there's a constant feedback loop with the customer or product owner to ensure that the development is aligned with their needs.
Agile is becoming increasingly popular, isn't it?
It is. It's a very effective approach for projects where the requirements are likely to change frequently or where there's a high level of uncertainty.
And it's particularly well suited for developing web and mobile applications where rapid innovation is crucial.
Now, shifting gears a bit, we came across a distinction in our research that often causes confusion. Quality assurance, QA, versus quality control, QC.
Oh, yes. These terms are often used interchangeably, but they actually have distinct meanings.
Exactly. It's an important distinction.
So can you shed some light on the difference between QA and QC?
Absolutely. Quality assurance, or QA, is all about preventing defects from occurring in the first place. It's about establishing and continuously improving the processes and practices that are used to develop software.
So it's about building quality into the entire development lifecycle.
Right. It's a proactive approach that focuses on things like establishing coding standards, conducting code reviews, implementing robust testing practices, and providing adequate training for developers and testers.
So it's about setting up the right environment and the right processes to minimize the chances of errors happening.
Exactly. Quality control, or QC, on the other hand, is more focused on detecting and fixing defects that have already occurred.
So it's more of a reactive approach.
Right. It involves activities like testing the software to identify bugs, reporting those bugs to the development team, and verifying that those bugs have been fixed correctly.
So QA is about preventing defects, and QC is about finding and fixing them.
Precisely. Now, moving on to another important aspect of software development, the environments where the software is developed, tested, and ultimately deployed.
Right, the different software deployment environments.
Exactly. These environments are essentially different stages or setups where the software resides during its lifecycle.
And the specific names and configurations of these environments can vary from one organization to another, right?
Oh, definitely. But there are some common patterns and conventions.
Can you describe some of the most typical deployment environments?
Sure. One of the most basic is the Locale environment. This is simply the developer's own personal computer where they write and initially test their code.
Their own private sandbox where they can experiment and make changes without affecting anyone else's work.
Exactly. And as part of this individual work, they might use specialized tools called test harnesses, which are like mini testing environments that allow them to isolate and test specific parts of the code. Or they might use unit testing frameworks, collections of tools that simplify the process of writing and running these localized tests.
Right. So it's a very self-contained environment for individual development and testing.
Right. Then, once a developer has completed a piece of work, they'll typically push their changes to a shared environment, often called the DEV, or development environment.
This is where multiple developers integrate their code changes and work together to build a more complete version of the software.
Exactly. The DEV environment is constantly evolving as new features are added and bugs are fixed.
But it's understood that it's a work in progress and may not be completely stable or bug-free.
Right. Then there's the test environment, which is specifically set up for the dedicated testing team to run their various tests.
Ideally, this environment is kept separate from the DEV environment to avoid any conflicts or interference with the testing process.
Exactly. Testers often have specific test data and configurations that they need to use, and it's important to keep that separate from the development environment.
So it's a controlled environment for executing those test cases and verifying the software's behavior?
Right. And then, as we get closer to releasing the software, we have the pre-prod environment, also known as the stage or staging environment.
This is like the final dress rehearsal before the software goes live.
Exactly. The pre-prod environment should closely mirror the production environment, the live system that users will actually interact with.
So they're trying to simulate the real-world conditions as closely as possible.
Right. And the purpose of this stage is to conduct final, comprehensive tests, including performance testing under realistic loads, to make sure that the software is truly ready for prime time.
And once everything checks out in pre-prod, the software can finally be deployed to the pre-RD or production environment, the live system that users actually use.
Exactly. That's when the software becomes accessible to the general public. Now, earlier we touched upon the fundamental principles that guide effective software testing.
The core tenets that underpin this whole quality assurance endeavor.
Right. So let's dive into those principles in more detail. What's the first one?
The first principle is testing shows the presence of defects, not their absence. What this means is that even if you execute thousands of tests and don't find any bugs, it doesn't guarantee that the software is completely bug-free.
It just means you haven't found any bugs yet.
Exactly. Testing can significantly reduce the probability of bugs being present, but it can't definitively prove that there are none lurking somewhere in the code.
Right. It's kind of like trying to prove that there are no black swans by looking at 1,000 white swans.
It's impossible to be absolutely certain.
What's the second principle of testing?
The second principle is exhaustive testing is impossible. In other words, you can't test everything. There are simply too many possible inputs, combinations, and scenarios to test every single one.
It would take forever.
It would literally take an infinite amount of time. So testers have to be strategic. They have to prioritize and focus their efforts on the areas that are most likely to reveal bugs.
And there are various techniques for doing that effectively.
Right, like pairwise testing, which focuses on testing all possible combinations of pairs of input parameters rather than trying to test every possible combination of everything.
Which would be a combinatorial explosion.
Exactly. And that leads us to the third principle, early testing.
This one's pretty self-explanatory. The earlier you start testing in the development process, the better.
The cost of finding and fixing a bug increases exponentially the later it's discovered.
It's much easier and cheaper to fix a bug during the design phase than it is after the software has already been released to the public.
Absolutely. Early testing can save a lot of headaches down the line.
What's the fourth principle?
The fourth principle is defect clustering. This principle recognizes that bugs tend to cluster together. A large percentage of defects are usually found in a small number of modules or areas of the code.
It's like the Pareto principle applied to software bugs. 80% of the bugs are in 20% of the code.
Exactly. So testers need to identify those high-risk areas and focus their efforts accordingly.
Right. And this is especially important for critical systems, like banking software, where even a small bug can have huge consequences.
Absolutely. Then we have the pesticide paradox, which is the fifth principle of testing.
This one's a bit more metaphorical.
It is. The idea is that if you keep running the same set of tests over and over again, you'll eventually stop finding new bugs.
It's like using the same pesticide on a field for too long. The pests eventually develop resistance.
Right. So testers need to constantly be coming up with new and different test scenarios to avoid this pesticide paradox.
They need to keep things fresh and unexpected.
Exactly. What's the sixth principle?
The sixth principle is testing is context dependent. What this means is that there's no one-size-fits-all approach to testing.
The way you test software will depend on a variety of factors, such as the type of software, its intended use, the target audience, and the level of risk involved.
Right. A mobile game will be tested very differently from a medical device.
And finally, we have the absence of errors fallacy, which is the seventh principle of testing.
This one's really important to remember. Just because you don't find any bugs during testing, it doesn't mean that the software is perfect or that it will meet the needs of its users.
It could still be difficult to use, or might not solve the problem it was designed to solve.
Right. Ultimately, the true test of software quality is whether it's usable, useful, and meets the expectations of its users.
Now, let's move on to the different levels of testing, how testing is structured and organized based on the scope and granularity of the software being tested.
Right. These levels represent a sort of hierarchy of testing, starting with the smallest units of code and gradually expanding outwards to encompass the entire system.
What's the most fundamental level of testing?
That would be component testing, which is also often referred to as unit testing.
This is where individual components of the software, things like functions, modules, or classes, are tested in isolation to verify that they're working correctly on their own.
Right. It's like testing the individual bricks before you start building the wall.
And this level of testing is typically performed by the developers themselves as they're writing the code.
Exactly. It's a very granular and technical level of testing.
What comes next in this hierarchy?
Next is component integration testing, which focuses on testing the interactions between those individual components once they've been integrated together.
So it's like testing whether the bricks fit together properly to form a stable wall.
Right. It's about making sure that the different parts of the software can communicate with each other and work together seamlessly.
Then we move up to system testing, which is where we test the entire integrated system as a whole.
Right. This involves testing the complete functionality of the software, including all the different user workflows and scenarios.
So it's like testing the entire building, not just the individual bricks or walls.
Exactly. And system testing also includes testing non-functional aspects like performance, security, and usability.
Those are critical for ensuring a good user experience.
Absolutely. And then there's system integration testing, which specifically focuses on testing how the system under test interacts with other external systems or services.
So if our software needs to communicate with a database, a payment gateway, or some other third-party service, that's where system integration testing comes in.
Exactly. It's about making sure that all those external connections are working as expected.
And the final level in this hierarchy is acceptance testing, which is the last stage of testing before the software is released to the end users.
Right. This is where we get the stakeholders, including the actual users involved, to make sure that the software meets their needs and expectations.
It's the final validation before the software goes live.
And there are various forms of acceptance testing, such as user acceptance testing, UAT, operational acceptance testing, OAT, and beta testing, each with its own specific focus and objectives.
Now, moving on to types of functional testing, the different ways in which we test the software's features and functionalities to make sure they're working as intended.
Right. Functional testing is all about answering the question, what should our product do?
It's about verifying that the software has all the features that were specified in the requirements and that those features work correctly.
And this can be approached from a couple of different perspectives. Black box testing, where you test the software without knowing its internal workings, and white box testing, where you actually examine the internal code structure and logic.
Let's start with black box testing. What are some common types of functional testing that fall under this category?
One very common type is smoke testing. This is a quick, high-level test that's performed after a new build of the software is created to make sure that the most critical functionalities are working at a basic level.
It's like a quick sanity check to see if the software is even worth testing further.
Exactly. Then we have critical path testing, which focuses on testing the functionalities that are used most frequently by typical users.
So the core user journeys, the essential workflows that people use day in and day out.
Right. We want to make sure those are rock solid.
Absolutely. And what about extended testing?
Extended testing is a more comprehensive and thorough approach to functional testing. It involves testing all the functionalities that are specified in the requirements, including less common scenarios, and even negative tests, where we deliberately try to break the system by providing invalid or unexpected inputs.
It's about pushing the boundaries of the software to see how it holds up under different conditions.
Exactly. So that covers functional testing, which is all about what the software does. But we also need to consider the how well it does it.
Right. That's where non-functional testing comes into play.
Non-functional testing is concerned with the quality attributes of the software, such as the performance, reliability, security, usability, and so on.
It's about making sure that the software not only does what it's supposed to do, but also does it well.
What are some key types of non-functional testing?
Well, performance testing is a big one. This involves a whole range of tests designed to assess how the software performs under different loads and conditions.
We want to make sure that the software is responsive, that it can handle a large number of users, and that it doesn't crash under pressure.
Right. And within performance testing, there are various subtypes, such as load testing, stress testing, stability testing, and volume testing, each with its own specific focus.
Then there's installation testing, which verifies that the software can be installed and configured correctly on different platforms and devices.
Usability testing is also crucial. It's about making sure that the software is easy to use, intuitive, and provides a good user experience.
Security testing is another critical area, focusing on identifying and mitigating any security vulnerabilities in the software.
And then there's localization, L10N, and internationalization, I18N, which are all about adapting the software to different languages and cultures.
And finally, accessibility testing is about ensuring that the software is usable by people with disabilities, complying with accessibility standards and guidelines.
So non-functional testing is a really broad and important area of software testing.
Absolutely. Now, there's another important distinction we need to make: validation versus verification. These terms are often used interchangeably, but they actually refer to different aspects of software quality.
Can you elaborate on that distinction?
Sure. Validation is about making sure that we're building the right product, that the software we're creating actually meets the needs and expectations of the customer and end users.
So it's about ensuring that the software is fit for purpose.
Exactly. Verification, on the other hand, is about making sure that we're building the product right, that the software is developed correctly according to the specifications and quality standards.
So validation is about the what are we building the right thing, and verification is about the how are we building it right.
Precisely. Now let's shift our focus to testing based on code execution. The two main categories here are static testing and dynamic testing.
What's the key difference between these two approaches?
The main difference is whether or not the code is actually executed during the testing process.
So static testing is about analyzing the code without running it.
Right. It involves activities like code reviews, where developers manually inspect the code to look for potential errors or vulnerabilities.
And also things like analyzing the software's design documents, requirements specifications, and test plans.
Exactly. It's all about catching potential problems early in the development process before they actually make it into the working software.
And what about dynamic testing?
Dynamic testing, as the name suggests, involves actually running the code to observe its behavior.
So this is where we actually interact with the software, clicking buttons, entering data, and seeing how it responds.
Exactly. And it encompasses all the different levels and types of testing that we've discussed so far, from unit testing to system testing to acceptance testing.
Now, let's consider testing based on testers. We have alpha testing and beta testing, both of which involve getting feedback from actual users.
What's the distinction between alpha and beta testing?
Alpha testing typically happens earlier in the development process and involves testing within the development organization itself, often with developers, testers, and other internal stakeholders.